So I'll share my screen, and this is the notes that I've issued to you before, and we've talked about supply air diffusers mainly. We didn't get to talk about exhaust and return air grills, or louvers, if my recollection is correct. So we'll just have a bit of a talk about those, and I'll skim down to return air, exhaust air grills, relief air grills. You can have egg crate, egg crate, ceiling grills or wall-mounted grills, half chevron ceiling or wall-mounted grills, linear bar grills. Linear bar grills are often used for supply air in residential developments, and they look nice. Architects like them, but you can also use them for return air. Linear slots normally used for supply air as well, but in a boardroom or fancy room that the architect wants something special on the ceiling, they can be used for return air. So instead of having the direction bars inside the linear slots, you just take them out, and it's just an open grill for return air. You can have mesh grills, which are often used in car park exhaust systems, perforated face grills for return air and exhaust air in specialised applications, normally laboratories, hospitals and prisons. So you can get secure perforated face grills specifically for prisons and mental health jobs. And the reason they use them is they call it anti-ligature, which means they can't put a strap around the grill and tie it around their necks. It sounds a bit awful, but that's how it is, and that's what they're made for, to prevent people from committing suicide in those situations. And door grills. So I'll just refer you to, so this is in your files, the shape air data. This is pretty comprehensive information. We had a look at this before when we talked about supply air grills. So section 2 on grills, I'll just open that. And then there's this whole list of different types of grills. So we'll just quickly go through that and show you the different types so you know what you're looking at. So this is the door grill. You've heard of door grills. They're used for relief in and out of closed rooms. So if you're supplying air to a room, you probably use a door grill or a door undercut to let the air come back out again. And this goes back to air balance we've talked about. So door grills are commonly used for that air relief in that situation. You can get an acoustic door grill. We don't use them very often, but if you really want to get some noise control, if you don't want people to be able to hear what's being talked about in an office, for instance, you can use an acoustic type door grill. There's an intumescent, so this is a fire rated door grill. If you've got a room that's it's a fire rated room, like a switch room or something like that, you can use these grills, which have an intumescent material. If there's a fire in the room, the intumescent expands and seals the room. So again, they're not used very often, but I have used them in certain situations. A light-proof door grill, vandal resistant. So if you don't want people climbing in through door grills or whatever, you can get those. Now these are the return air and exhaust grills, normally egg crate grills. You've probably heard of those. Yep. These are probably the most commonly used exhaust or return air grill. They've got the highest free area, open area, and they're the cheapest. Oh, and by the way, for each of these pages, you can scroll down and get all the data on these grills. Okay, so this is why this is a good reference, because it's got all the dimensional data, It's got performance data and how to select the right size grill for your situation. And remember that I was going to say the BCA, it's now called the NCC, National Construction Code, has requirements on pressure drops through grills. We talked about that last time. So I'll just quickly go back to that relevant part. So this is J6D5, section J in the NCC, and points J, K, L, M refer to grills and allowable maximum pressure drops in the index run. So if a grill is in your index run, you can't exceed these pressure drops. Supply air diffusers and grills, 40 pascals. Exhaust grills must not exceed 30 pascals. Transfer ducts, 12. Door grills must not exceed 12. So with that selection data, you can go through and pick the right grill to be below that pressure drop. So having mentioned that, with your static calcs, Jess, you've got to take, I think that there are defaults in the spreadsheet for these pressure drops. But if you look at it, if you do an actual selection, you can always get well below that allowance. So you don't want to go too far overboard with your calculations because you'll finish up with a number that's too high.
So, okay, I spoke to Hudson about it and he said just take the NCC allowable maximum. Do you think there's another way? Like, what's the other way to sort of ballpark estimate that?
Well, let's just do a selection on a grill. Just go into the shape air data, for instance. The problem is there's no guarantee that the contractor is going to use shape air equipment. They'll select something else. But if they're going to use a supply air diffuser or any return air grills, they're probably going to use egg crate grills for return air. So it's whether you use shape air or somebody else, it's not going to make much difference. So if you select the right size for the airflow, and then have a look at what the pressure drop would be in that situation, that would be the number that I would use. And,
right.
And I noticed that Hudson said that Ivan was keen for you to use the error tables rather than just use the numbers that come up in the spreadsheet. So, and
yeah,
I
understand
why he wants you to do that, because that gives you a better feel for how these things come about, how you calculate these things, rather than just put a plug number in there. But if you've got lots and lots of static calcs to do, it's going to take a long time to be looking up these values all the time. But I think it's worth doing it once or twice just to get a feel for the first principles, if you like, of how it's worked out. And then you can start to use your judgment a bit. If it says the maximum allowable pressure drop for a diffuser is 40 pascals, you might say, well, actually, no, I think that's too high. I think it should be about 25, because you've done it before and you understand what it really should be for the right selection. Because if you're allowing the NCC maximum values right through, and then you add another 10% at the end, you could end up with a static that's just way too high, and you're not selecting the best fan for that situation.
Right.
Does that make sense?
Yep.
Okay, let's go back to shape air. So we'll keep looking at some of these. Yeah, so there's some performance data there. Egg crate quick fix. These are a bit repetitive, but they're just different styles of grills. Site resistance. So that's an egg crate that's, I guess, the louvers are tapered over a bit so that you can't see straight through. They're not used very often. In fact, I don't think I've ever seen one. That's a half chevron grill. This is quite common for return air. You can use them in a ceiling, but quite often in a wall, you'll see these sorts of grills because you can't really see through them. And they look a bit better than an egg crate, but so that's commonly used. This is a mesh grill, which is obviously very open, quite often used in car park exhaust systems, because no one's going to worry if you can see through the grill in a car park exhaust system. And these are quite cheap. and they have very low pressure drop. So you can imagine if you select these to be the right size in terms of the velocity through the grill, the pressure drop is very low through these types of grills. It's not going to be 30 or 40 pascals. It might be 5 or 10, probably not even that. This is a perforated grill. It's one style. They come in different hole sizes. So depending on the application, you can select a different hole size. Now that might be a laboratory or a hospital application. Then you've got a perforated security grill, which I mentioned before, which has got very small holes. They call that anti-ligature. Now these are getting back into supply air grills now. So a single deflection grill. This would be mounted in a wall or on the side of a duct, if it's an exposed duct, for supply air. Can be used for return air as well, but not normally. Then you have double deflection. So you've got two sets of blades, horizontal and vertical, and they can be adjusted up and down or sideways to get the sort of air pattern that you want. And they can be adjusted on site. They're a bit fiddly because you sort of have to move each one individually, but that can be done. Single deflection grill, high volume, so that's a more open type supply air grill. Double deflection, high volume. Again, you've got two sets of blades, but a bigger open area. And there's a curved face grill, which you might have seen these in a supermarket, say Woolies or Coles sometimes have exposed circular ductwork in the supermarket. Sometimes they put a box that comes out of the duct and they put a straight grill on it, but other times you might see a curved face grill. So they can be made to suit the radius of the duct and fit flush onto the duct surface. They look a bit nicer, but they do cost a little bit more as well. So that's a quick introduction to the types of grills that are available. And weatherproof louvers is another important part of what we do. They're normally rectangular, but you can get them in round shapes as well. And sometimes an architect might want a round louver on the building, so you can get them. They're used for outside air intakes. You can have single or double stage mounted in an external wall. And usually with louvers, they're quite often supplied by the builder. So we're a little bit out of the loop here, but we have to get involved in making sure they're selected correctly, because if they're not, and I have seen situations where a contractor has put in a louver which was dictated by the architect. They said, we want this size, it fits in our design. It wasn't big enough, and it caused the contractor all sorts of problems because there was pressure drop, there was water being dragged into the building because the velocity was too high. You know, it's quite an important thing to be aware of. So as we go through this session, I'll give you a few tips on how to select them. Exhaust air discharge louvers, they're normally just single stage. With the outside air intake, you've got to be aware that if the velocity is too high of the air coming in, there's a chance that if it's raining outside, you can actually drag the water into the building. So you've got to get the velocities right to prevent that happening. They're used for plant room ventilation louvers, and there's a penthouse arrangement for very high airflows in the roof. Now that used to be quite common years ago. It's not so common now, but you can still buy these, and they can be quite effective if you've got a high volume that you've got to drag through a roof. So once again, I'll just go back to the shape air information and show you some louvers. Go back to here. So there's a section here on weather louvers. So that's what they call a large weatherproof louver. Again, for each of these selections, there's all this data on dimensions and performance and so on you can have a look at. So if you have a louver, you can go and have a look at that, and it's quite good information to help you select them properly. You can get them indoors like that. You want to have a ventilated door. Here's the penthouse thing that I mentioned. So it's just a box that sits on the roof with louvers all around. So they're, if you've got high volumes, they're quite handy and low profile. Obviously, in this case, you haven't got a wall to drag the air through. You've got to take it through the roof. So that's a good selection. Side assembled, that's pretty rare. Small ones, you just need to be careful with small ones when you select them because they have a relatively low free area. And we'll talk about that a bit more shortly. And you can get round ones. And these are a bit limited in size, I think, I guess they can make any size that you want, but the standard ones look like they're, quite small. And that's normally what they're used for. If you've got an exhaust, say a toilet exhaust or something, and you're using a round duct, they can work out quite well, but normally it's just an architectural requirement. If they want a round louver, you can get them. Excuse me, otherwise we wouldn't use them. Okay, let's go back to the notes. So selection criteria, we talked about that last time with supply air diffusers. Specific criteria for return air grills, exhaust grills, etc. Obviously the airflow rate is the starting point. What sort of sound level are we trying to achieve in the space? And that performance data that I've just been talking about has the noise ratings for the different sizes. So noise rating is going to be one of the main selection criteria. If it's an office space, for instance, your NR might be, let's say 35 dB. So you want to select your grill so it's less than that, within that range. You don't want to select it for 50 NR because it'll be very noisy, which is just an indication that the velocity is too high. So all these things relate. Okay, velocity causes pressure drop and it causes noise. So you need to be in the right range. Typically, the velocity through a return air grill, an egg crate grill, would be around probably 3 to 4 meters a second at the most. But it might be lower than that, and the lower the better. Obviously, pressure drop. What type of grill do you want? What's the architect want in the ceiling? It's usually, if there's an architect involved, they will probably have their requirements for the types of grills that they want to see on the ceiling. So you need to follow their requirements. The material you want to use, you can get plastic ones, but they do look cheap, but they are cheap. Usually it's aluminium or steel, and they're more robust, obviously, and cost. Plenums and cushion heads, talked about that last time. The weatherproof louvers specific criteria. I mentioned before, architectural or builder requirements normally dictate these because the louvers are in the external walls. It's unusual for the louvers on the outside of the building to be included in the mechanical services contract because they're an architectural feature. Now this creates a little bit of an issue for us because we want to know what the pressure drop is, what the size of the louver is, and so on, to suit our system. So we've got to try and have some input to this to guide the architect or the builder on the sizes. So just be aware that sometimes they pick the wrong size, and we need to tell them that they need to be bigger to suit the design. Airflow rate's the starting point. Again, sound level is important. Velocity, again, creates sound. we need to know the next size. The next size will be the duct connection size. If there's a duct or a plenum on the back of the louver, which there quite often is, that will be the next size. Pressure drop, materials, colours. You can get different colours, obviously, because they're on the external side of the building. The architect might want a colour that matches the building colour, or might be something completely different. We'll go down to here. Return and exhaust grills are positioned strategically to avoid disturbance or direct scavenging of the supply air and to minimise the amount of return air ductwork required. So what I mean there, to avoid disturbance or direct scavenging of the supply air, you don't put it right next to a supply air diffuser or in between two supply air diffusers, because the air's coming out of the supply air diffuser, and because there's a negative pressure at the return air grill, that supply air might be drawn straight out, or a portion of it. So you want to offset the return air grill so that the air in the room has had a chance to, or the supply air has had a chance to mix up the return, sorry, the room air, before you take the return air back out again. And we don't want to have return air grills all over the place, because it's not necessary. So for small systems, you probably only have one return air grill. You might have, or you will have multiple supply air diffusers. You might, let's say you have 10 supply air diffusers, you probably only need one return air grill. And you put it as close as you can to a fan coil unit or to the plant room, so that you minimise the amount of return air duct. So that's what I've said there. Okay, we always try to achieve the most efficient and cost-effective duct design. And just be mindful as well that, and we're going to talk about acoustics a bit more in later sessions, but with supply air, because you have multiple supply air diffusers, the sound power that's coming out of the fan coil unit or air handling unit is distributed amongst all those supply air diffusers. So you have less noise coming out of supply air diffusers than you will out of the return, because if you only have one return air grill, all the sound power from the motor is coming to that one return air grill. So sometimes you need to internally line the return air duct to get some attenuation. Does that make sense? That you've only got a relatively short length of return air duct. You've only got one grill, so all of that sound power on the inlet side to the fan is going to that one return air grill. Okay, we'll talk a bit more. Or look, before we go on, any questions up to that point?
No.
Okay. Have you talked much about grills with Philip and Ivan at this stage?
Yeah, we've spoken maybe more from like a drafting side. Actually, no, engineering side as well. About like throw and lander effect. Yeah.
Yeah, right. Okay, so maybe what I'm talking about here is going over it again, but I hope this is helpful to you anyway.
Yeah, still helpful.
We'll talk about weatherproof louvers a bit more now. So they're available in single stage and two stage. Single stage is most common. Two stage is pretty uncommon, but they are available. The single stage louvers have one set of horizontal blades for the air to pass through, whereas two stage louvers obviously have a second set of blades. So normally you have looking at the front of the louver, it looks the same. You've got the horizontal set of blades, but behind there's a vertical set of blades. And the reason that they use them in some situations is if it's on a if you've got very windy or wet environment, the two stage helps to prevent that moisture getting into the building. But they do have a pretty high pressure drop. But we're just going to focus on single stage louvers because they're the most common. So the air pressure drop across louvers can be significant and increases with the number of stages. So just a quick look at the NCC again. So coming down here to D, this is J6D5 again. It does stipulate the allowable pressure drops for louvers. So for single stage 30 pascals, 2 stage 60, acoustic louvers 50 pascals. Now I'll mention acoustic louvers in a minute. And for other non-weatherproof louvers, still 30 pascals, which is the same as exhaust grills, 30 pascals. We'll come back to acoustic louvers. I'll talk about them as we go down. I've got a bit of info here on how to select louvers. So as I said there, the NCC specifies maximum allowable pressure drops. Single stage louvers generally have a free area ratio around 50%. But the free area is dependent also on the louver size. So if it's 50% free area, this means that the air velocity, the face velocity, which is the neck velocity, if you like, the duct size at the back, at the face of the louver doubles as the air flows through. Okay, because if your free area is 50%, it means that you're accelerating the air, you're doubling the velocity of the air as it passes through the louver. Yeah. Small louvers tend to have free areas less than 50%, so you need to be careful with those. So just I'll just explain as I go through. Example, if the face velocity at the intake louver is 1.5 meters per second, so that's the gross area of the louver or the neck area at the back, then the passage velocity will be around 3 meters a second with a louver of 50% free area. So that's in my career, that's been the rule of thumb for me. If you've got very small louvers, it's a different thing. But for reasonably large louvers, you work on a free area no more than 1.5 meter. Sorry, face velocity no more than 1.5 meters per second, and that will usually be pretty safe with all the manufacturers' louvers. So there's some reasons for doing this. Firstly, it's generally accepted that air travelling at 3 meters a second is on the threshold of carrying entrained water in the event of rain. For this reason, we want to limit the louver passage velocity to 3 meters a second maximum. So when you're bringing air in, you don't want the passage velocity to be more than 3 meters a second because moisture will be caught up in the airstream and will come into the building. And then you're going to have leaks. Okay, that's going to get into the ductwork or it's going to get into the plant room and there's going to be water on the floor. If it's a louver in a wall that's connected to a duct that's above an occupied space and water is coming in, eventually it's going to leak out of the duct and it's going to drip on the ceiling and, you know, that will have to be rectified. So we want to get those sizes right to prevent these things happening. In general, single stage intake louvers should be sized for a maximum face velocity of 1.5, assuming a free area of 50%. If you look at that shape air data, it actually gives you, for the different size louvers, it tells you what the free area is. So if you're 50% or less, you're pretty safe. I wouldn't select anything above 50% free area. And as I said, beware when selecting small louvers as the free area ratio may be relatively low, which causes a high passage velocity and a high pressure drop. So you might select a small louver. When I say small, I'm talking about sort of 300 by 300 and less, which you might use in a residential situation. You might work on a face velocity of 1 meter a second. But have a look at the data and see what the free area is. So a lot of these things are linked over history of experience over the years. It often turns out that a face velocity of 1.5 meters a second will cause a pressure drop of about 30 pascals. so the compliance with the NCC is achieved. So that data in the NCC is based on experience of the people who've written that code. These are just facts of nature, if you like. It's just how it works. And they become rules of thumb for design. The pressure drop across the louver is proportional to the square of the air velocity, which applies for everything. As I said before, building designers will often push to reduce louver sizes. So architects or builders, because they don't want to see the louvers, they don't want to see anything. They just want air conditioning to happen. But we have to have grills and louvers and these things to make it work. So we need to push back where necessary and stick with the fundamentals. Otherwise, we'll have issues that have to be resolved and can be very difficult to resolve. If the building gets built and finished and the louvers aren't big enough, well, the contractor who installed the job is going to have problems. And it'll be pressure drops, it'll be noise, water ingress, and so on. And once the louver's built in, well, what can you do? You can upgrade fans if you have to, but then that's going to create more noise and create more water issues. So acoustic louvers are designed to absorb the sound of equipment housed in a ventilated enclosure, like a plant room. So they're often used for plant room ventilation where noisy equipment is located inside, such as chillers, pumps, large fans, air handling units, and so on. I'll show you a picture of some of those. So this is from the Fantech catalogue. This is a curved blade acoustic louver. Their depth varies. That one looks like that one's 200 deep. This is a fairly standard one with a flat face. These sections, the modules in there are actually internally insulated perforated panels with a metal face. So it's like an attenuator, but they're not as long as an attenuator. And these panels slope upwards so that the moisture, you've got to size them correctly, but so the moisture is not coming in. And if it does get on the face, it'll drain back out again. So that particular one there is they say 300 long. It's actually, well, I would call that the depth. The depth of the louver is 300. So if it's flush on the face of the building, it'll go back into the building by 300 millimeters less the depth of the wall. So if the wall is 200, it's going to stick into the room by another 100 mil. And it says dBA reduction 11 in that case. Then you can get a deeper one, which is 600 deep. And so you get more attenuation with that. That says a dBA reduction of 17. So if you're using acoustic louvers and selecting them, that gives you an indication of what sort of sound reduction you can get. But to select them correctly, you need to look at the whole sound spectrum. But we won't go into that now. We can talk about that in more detail when we get to that. Discharge louvers. So basically a discharge louver is the same thing as an intake louver, but they don't have the issue of potential water ingress because we're pushing the air out of the building in that case. But pressure drop is still an issue to be considered. And the NCC requirements of 30 Pascal pressure drop still applies. The NCC doesn't specifically mention discharge louvers, but it does say that 30 Pascals maximum for exhaust grills, so that applies. So just to finish off, in terms of energy efficiency and fan selections, it's important to minimise pressure losses where we can. Accordingly, it's recommended that the face velocity for discharge louvers doesn't exceed 2 meters a second, which will result in a passage velocity of around 4. So in this case, that's okay because we're pushing air out, we're not dragging air in, and that will keep the moisture out of the building. but as the velocity increases, the pressure drop goes up exponentially. So just be aware of that. And you can see when you look at the shape there performance data, you can see what the pressure drop's going to be. It has got curves in there for velocity, face velocity, and pressure drop. And you'll see how quickly it goes up. So that finishes the discussion on grills. Any more questions? Anything at all?
All good from my side.
All right. Well, as I said, next time we'll talk about pump pressure calculations. Some of these things that we're talking about, I think grills are very relevant to what you're doing, because when you're drafting, you'll always have grills, and you'll always need to think about the sizing of them and the way they're laid out, and the best duct layout that you can come up with, the most economical duct layout. But pump pressure calculations, I'm happy to, I've prepared a session, I've already sent it to you. I'm happy to go through that with you. It's very similar to fan static calculations with different elements in the system. But the best way to really get familiar with these things is to put into practice. So to start doing some calculations. So I guess I'll let Philip know when we've done that session, and I think you guys should as well, because if someone is doing a job, if Hudson's on a job, or Chock, or someone is doing a job with pumps, they might ask you to do that calculation so that you can get some practice and start to make some sense of what we're talking about. Because it's like, you know, like when you go to lectures at uni, they talk about stuff, and it just goes over your head until you have to go back and study for an exam in some cases. So the best thing is to put these things into practice. And with pump pressure, I know that the terminology is pump static calculations. That's not strictly correct. It's I call it pump. I just call it pump head calculations or pump pressure calculations, because you're really calculating a dynamic pressure in a pump system. The static head on a pump is, if you've got a pump down the bottom of a building and you've got water pipework that goes all the way up the building, the static head is the head of that water above the pump. But when the pump is turned on and it's pushing water through a system, it's a dynamic pressure. So that's what we're going to be calculating. And that'll be the basis for pump selections, which we'll go on to after that. So everything we do is basically a process. I don't know if I've said that before. I tend to harp on about processes, but all the work we do is a process. So with your fan static calcs, you know, there's a process of sizing the ductwork, laying out the diffusers, and then doing the static calculations, and then trying to optimize that to get the best results you can. Maybe you change the ductwork a bit to make a more efficient ductwork design. And then you can select the fan, and you've selected the fan, and you can go on to working out your electrical requirements and your control requirements, and it's a whole process that goes along, and it applies to all these things that we do. There's the very first video I think that we ever did was talked about this industry and the process. Have you guys seen that?
Yeah.
Yeah.
So I think that's probably a good introduction to how the industry works and the processes that we follow. But that's about it, I suppose, for now. I can let you go. There's no point really getting into anything else at the moment. Well, one other thing. Have you looked at filters at all? Have you done any filter selections?
Not yet.
Briefly, for FCUs.
Okay.
I don't think I have.
I've got a session prepared on filters as well. which I was going to do after we did the grills, but with the sessions that Philip's doing with you, it's changed it around a little bit. So I'm just sort of working in with him to suit his program. So probably after we do pump pressures, we'll have a look at filters, because that'll be very relevant to what you're doing with fan coil units, air handling units, or other ventilation systems that have filters. So I think that's probably worth doing as soon as we can. All right. Well, thanks for attending, and I'll see you in a few weeks on the
Thank you,
14th of May.
Peter.
Thanks a lot, Peter.
Enjoy your
Enjoy
trip.
your time off.
Thank you.
Have a
Okay.
great time.
All the best. See you.
Take care. Bye bye.
Bye.